Okay, let's begin. Welcome everyone to the Astronomical Society of Edinburgh, wherever you happen to be. I've just got a few slides up front to tell you what's happening, and then we'll get on to the main event of the evening. So I've just got a few news items, what talks we've got coming up in the next month. And then our main talk of the evening is from Luna Zagorac, who's in Ontario, Canada. I hope I've not said your name wrong, Luna. About digital skies for ancient contexts, using Python to investigate stellar data from Ramesside Star Clocks. Sounds really interesting. Looking forward to that. I just wanted to mention a new article that Neil Martin and a few others have written that's now on our website. Neil, can I get you to introduce this? I mean, we are a smart scope society in many ways now, and Neil's been leading the way on that. Do you want to tell us about your article, Neil?
Yeah, absolutely. Thanks, Mark. Yeah, everyone knows I'm a bit of a fanboy of smart telescopes, and Mark's made a few comments along the way about, well, what else can we do beyond imaging? So we threw some ideas around about what we could write about, and with a lot of help from Pat Devine, Douglas Higgy, Ramsey McIver, and some contributions from Mike Christie, we pulled together an article that describes what next with smart telescopes. So once you've captured some images using the standard approach, what else can you do? And so this article covers the sort of things you can challenge yourself with to go beyond the basics. So thanks to the guys for their contribution, and I had a lot of fun pulling it together.
Yeah, so thank you, Neil. So that's now on our main website. I'll put it in the newsletter on Sunday as well, a link to that. But I don't want there to be a lot of ASC smart scopes on the market next Christmas because you've run out of things to image. I want you to keep on doing useful astronomy with them. So that's the idea behind it. Just the next month, these are the talks that we've got coming up on the 5th of July. Stellar Winds, Givers and Takers of Life, Dr. Brad Gibson. That will be a hybrid meeting, so we will be at the AUC in Edinburgh, the usual place, Augustine United Church, and it will be on Zoom for members who can't make it, and also on YouTube for visitors as well. I believe that one actually will be given remotely, potentially from Canada as well, I think. I'm not quite sure, certainly from abroad anyway. On the 12th of July, we'll have our online monthly imaging and observing group meeting. That is for ASC members, and there's a lot of stuff going on in the society, lots of projects. That's really interesting at the moment. And on the 19th of July, the Universe Reality or Simulation, we have our honorary president and Astronomer Royal for Scotland, Professor Catherine Hayman. She'll be giving us that talk, and she'll be that's an online talk. As you know, Catherine is really suffering from long COVID, and this is the first time we've been able to get her back to give us a talk. So that should be interesting. And then we have our August break. So we've had a really busy year again, lots of good stuff going on. I think we could all do with a break. So that's what we'll be doing with the next month. Hopefully you'll get a holiday as well. That is really it for me. I'm going to stop the share and pass that over to you, Luna. So looking forward to your talk. So take it away. Thank you.
Okay, lovely. Thank you so much. Yeah, thanks again for inviting me and for having me. I'm really excited to talk to you all today, and I hope you find this presentation interesting and sort of edifying. One might consider that because it's so interdisciplinary, one might consider this project to be sort of like a history presentation masquerading as an astronomy presentation, or an astronomy presentation masquerading as a history presentation, you know, depending on whose attention I'm trying to get. So either way, I hope you get something out of it. So, right, my name is Dr. Luna Zagorac. During my day job, I study things like dark matter at the Perimeter Institute for Theoretical Physics. But today I will be talking about digital skies for ancient contexts using Python to investigate stellar data from Ramesside Star Clocks. And this is a project along with Professor Sarah Simmons at McMaster University, which is also in Ontario. However, Professor Simmons is awesome and also originally a Brit. So she's sort of from your shores. Just thought I would put that out there. Right. Okay. So I want to start with the idea that the sky really is our window into the universe. I work at the Theoretical Physics Institute, and a lot of what we know about not just astronomy, but about physics in general comes from looking really deep into the sky. And so things that we can see include things like planets and stars in our own galaxy and newly formed stars, clouds of gas, galaxies from 13 billion years ago, right? That's especially new and exciting with the JWST telescope, and that's something that I've been thinking about recently for different research projects. And even our own black hole, if you've seen those, EHC images of Sagittarius A star and other black holes nearby, they're really, really breathtaking. And there's so much more out there, right? There's stuff that we can't even see in principle with our telescopes, and that's the stuff that I study in my day-to-day. I study a particular subtype of dark matter called an axion, and how it would sort of present on astrophysical scales and how it might make our universe look a little bit specific, and whether we see that in nature. But for this talk today, I also want to introduce the idea that our sky is also really our human heritage. And this is not something that, I'm so brilliant to come up with. This is something that UNESCO has stated. So the sky, our common and universal heritage, is an integral part of the environment received by humanity. Humankind has always observed the sky, either to interpret it or to understand the physical laws that govern the universe. So this is from a ways back. This is from the proclamation of 2009 as the International Year of Astronomy. But nevertheless, I still think that it's worth sort of like pondering and remembering. Simply because, we are all here today because we have a certain love and appreciation and fascination with the sky. And that has been true for humans since, as long as any of us have been around. So astronomy and world heritage are two very tightly coupled things, right? The solstice just happened. So in the UK, there was a big to-do, at Stonehenge and things like that. These are things that we still sort of like keep and are important to us. And I really love thinking about this because I love thinking about cosmology. Cosmology is the sort of subtype of astrophysics that I study. So it's the science of the origin and development of the universe and sort of all of the different components within it. That is what I got my PhD in. But the philosopher Tolman also said that the way cosmology is the way of making sense of our place in the scheme of things. And I just love that intersection. And I think that even though it might not seem obvious at first glance, this is like a really, really great way to have astronomy meet the humanities and the social sciences. So with that, let's get cracking. So I will present you with a bit of an overview of Egyptian star data, given that I'm talking to astronomers rather than Egyptologists here. So we'll start with a quick intro into history. Maybe you know something about this. If it's an interest of yours, maybe you haven't thought about this since like grade school. Either way, that is totally fine. But so what we think of as ancient Egypt had like a really long and varied history, starting from the pre-dynastic period, which is the 5th millennium BC to the 4th millennium BC, and then all the way to the Roman and Byzantine Empire, right? And so here I really highlight 3 periods that I think are sort of more commonly addressed in pop culture and stuff like that. And so they might be more familiar to you. That's the Old Kingdom, which is sort of 2600 to 2100 BC. The Middle Kingdom, which is sort of 2000 to 1630 BC, and the New Kingdom, which is about 1500 to 1000 BC. And if you need things to associate these with, so the Old Kingdom, when you think Old Kingdom, or when I think Old Kingdom, I think the pyramids of Giza. This is when the pyramids of Giza were built. So these are some of the biggest monuments, the last standing wonder of the ancient world, and something that most of us are familiar with in some way. The Middle Kingdom is maybe not referenced as much in pop culture, interestingly enough, even though this was really the golden age of Egypt. So this is where some of the most classical texts date from. The language was really at its peak. If you study, the Middle Egyptian language and hieroglyphs, you were studying Egyptian as spoken in the Middle Kingdom. And there were a bunch of pharaohs called Senusret, including this one. I really like them because they have this very specific art style with the like very baggy sort of like under eyes and the big ears, and looking sort of tired and weary from their rule, which anybody who's been to graduate school, at least I know I can really resonates with. And then in the New Kingdom, we have things like Tutankhamun, one of the more famous, images of ancient Egypt, but also a bunch of pharaohs called Ramses, including Ramses II or Ramses the Great, which may or may not have been the pharaoh sort of referenced in the story of Exodus in the Bible. So just to give you sort of a sense of the time scales involved here. So this is a pretty long time ago. And as we will see, that will have an impact on the night sky as we are studying it. The other thing I really want to quickly present is the geography. Again, you may or may not be familiar with this, but this is sort of an overview of some of the more famous monuments of ancient Egypt. So up here we have the pyramids and stuff like that I associate with the New Kingdom, or sorry, excuse me, with the Old Kingdom. But for today, we will really be concentrated here in what is Thebes or Luxor. Thebes is sort of the ancient name, Luxor is the new name, and the famous Valley of the Kings, and some of the more famous temples are there. So this is the River Nile. On the east bank, we have Karnak Temple and Luxor Temple that are still connected and beautiful today. And on the west, we have a lot of mortuary temples, including ones that will contain the data that I will present to you today. And so I'm showing you all of this because it'll come into our story a little bit later. So the Valley of the Kings is right here, for instance. And by the way, this is from the Theban Mapping Project, which is a really awesome online repository if you've ever been interested in anything like that and want to take sort of a virtual traipse along ancient Luxor and the Valley of the Kings and so forth. In two more places that I will point out here because they'll be important for the discussion is Abydos. Abydos is one of the sort of holiest temples in ancient Egypt that has been important throughout those millennia that ancient Egypt was around, and specifically is dedicated to the god Osiris. And I will point out Asyut, which is sort of slightly farther north. But we're, somewhere in the region of Middle Egypt for the length of this discussion. But that's all nice and well. What we really want to talk about is the star data of ancient Egypt, right? Let's talk about these observations that I've been promising you. So here I'm just going to narrow down to look at the Middle Kingdom and the New Kingdom. I'm sort of ignoring the second intermediate period in here, but I will tell you about 3 types of Egyptian star data that I've spent any time thinking about. So the first is called diagonal star tables or diagonal star clocks, though I do think that diagonal star tables is a slightly more correct term in this case. So these are lists of stars that we will get into in a moment that come from non-royal coffins, mostly from Asyut. So that's the northernmost point that I showed you there. And later at the Osirian ceiling, the Osirian is one of the temples at Abydos. And so this is from the later time. So this is sort of from the Middle Kingdom and into the later New Kingdom. These show up in some different ways. There's also the transit star clock, as it's sometimes called, which I will refer to as the Book of Newt, which also is attested in the New Kingdom on the ceiling of the same temple. And again, we'll talk a little bit about what these figures mean and how they represent the sky. And finally, as you may guess from the title of the talk, the Ramesside Star Clocks are the bit that I will be talking most about today. So they are found inside of the Valley of the Kings, which is why that's sort of the bit that I expressed in our little geographic romp through Egypt. And they are the latest of these sorts of representations of the sky. So they're from about 1150 BC. Oh, and I should say that I am operating under the assumption that these 2 first things sort of represent an idealized type of sky, a sky that is informed by the actual sky and the stars that we see above us, but there is also sort of important in ritualistic arguments, and so might be a little bit of a fudge about how the stars actually move. Whereas the Ramesside Star Clocks, we currently believe are really based on some sort of timekeeping and real honest-to-goodness observational data that we can sort of try to analyze and get at the idea of how these were used and how they were constructed and what the sky looked like to an Egyptian. So to start, diagonal star tables. So this is what that might look like if you're not looking at just a sketch. So this is an example from the inside of a coffin lid of an individual called Idi. It is from Asyut, where most of them come from. So they are found mainly on coffin lids. That's sort of what they are synonymous with. They're mostly from the Middle Kingdom. So remember, this was sort of that golden period of Egypt, mostly from Asyut, but also a few from Jebelain, Thebes, Luxor, and Aswan. So those are places mostly further south. And it is divided into 2 types. So there are 2 types of lists of star data. They're called K tables and T tables based on the name that is given to the first star or deacon in this case to appear. It probably has some observational basis, but again, it is fairly idealized. And so if I were to draw half of it, what it looks like is this. I didn't draw this. This is from a set of texts called Egyptian Astronomical Text by Nogebauer and Parker, which is a work from the 60s that is really foundational to studying Egyptian astronomy. So let's break this down a little bit. So first of all, what you might notice is there's a length of hieroglyphic text in the center here. So it is an offering formula for the individual who is dead, for them to be reincarnated in the next life, etc. And thanks to here, we know their names. So this is actually for a priestess named Ashit. I believe she was God's given the title God's great wife, but I'd have to double check. But so this belonged to a woman named Ashit. The other thing that we see here is this middle column that shows us some deities and some text. So this in particular deity is named as Sopdet, and this is named as Sach. Now, the reason this is really important to us because Sopdet is what they call Sirius, and Sach is generally taken to refer to as Orion. So they're sort of at the same time deities, but also constellations, and constellations that we're familiar with, which we don't have a lot of these. Now, maybe somebody can venture a guess for what this one is. It is maybe, I think, one of the more recognizable ones, but this is actually the foreleg, which we today know as the Big Dipper. So this is the Big Dipper. And finally, we have the goddess Nut, which is just a representation of the night sky. So just sort of immediately establishing, if all of the stars sort of in this table weren't enough, that this has some like very deep astronomical connections. So now let's zoom out and look at the actual text. It's a little bit overwhelming at first, but let's first look at what the columns and the rows represent. So the different rows represent the hours of the night. Now, in ancient Egypt, the hours are always referred to as the 12 hours of the night and the 12 hours of the day. And furthermore, there's some evidence that there were 12 hours of the night first, and the day only started to be referred to as having hours later. Now, to us, that might sound strange because we just had the solstice, which means that, our nights are super short right now. So surely they don't have 12 hours. And in the deepest winter, especially in places like, Edinburgh or Ontario, it's dark for a long time. So they have well over 12 hours. So when the Egyptians refer to hours, it's not necessarily a 60-minute interval. It's more that the time from sunset to sunrise is divided into 12 chunks. So the number of hours is constant, not the number of minutes in an hour. So this is a slightly different way to think about things, something to keep in mind. The other thing is that up here we have a number of columns that would go to higher numbers, but I'm showing you only half of them. So these represent the weeks. There would be 36 columns because a week in ancient Egypt is 10 days. So 10 times 36, that's 360 days. And at the end of that, there would be what's called 5 days upon the year, or 5 epigomenal days. So these were the days that were sort of just like added at the end of the year. They were considered to have very bad juju. And the Egyptians mostly dealt with them by having a bunch of parades and getting drunk for 5 years straight, which I think is great, and we should bring that back. But nevertheless, so let's look at how the actual data in here functioned. So these are all, drawings of the actual hieroglyphs that are there that name some of these stars, but they're named things like "He who is in the boat," which is a fine name for a star, but I don't know which star that is. Unlike maybe something like Sirius or the foreleg or the Big Dipper, that doesn't necessarily tell me. That doesn't point me to the star in the sky that this is. So there has been a fair bit of work done to try to identify these, but it's hard. But nevertheless, let's look at how they move around this. So let's choose this one. So this is represented with the 2 reeds here, which just kind of look like 2 lines. I just chose that one because it's kind of easy to follow, even if you're not necessarily trying to read the hieroglyphs. So what this is telling us is that this star, whatever it's called, in the first week of the year is in hour 9. It's doing something in hour 9. We don't know. In the second week of the year, it's in hour 8. In the third week of the year, it's in hour 7. And then it continues to hour 6, 5, 4, 3, 2, 1. And if we had the full line of the coffin, you would see it reappear in the lower left corner. So this is why these things are called diagonal star tables, because the stars do move in a diagonal pattern. For the most part, there are some what's called triangle decans, which are stars that just fill out sort of the remaining triangle in the lower left part of this. And so there's been some work done trying to identify these constellations. I myself have started with trying to work with this data specifically and try to identify some of these asterisms, but it does get really hard because it just doesn't quite move as the sky that we're used to. And so it may be completely the real sky and we're missing something, or it may be some idealized version of the sky. So nevertheless, we can move on to our second type of star data that I'm presenting here, which is the Book of Nut. Now, for completeness, I will say that the picture I'm presenting here is not the Book of Nut, it's the Book of the Night. But because I couldn't find a good picture of the Book of Nut, but it is called the Book of Nut because of the representation of the sky goddess Nut as seen here. And this is the Book of the Night from the tomb of Ramses VI, which is really gorgeously adorned and has a lot of really interesting astronomical bits. So the original title of this work that wasn't known until something like 10 or 15 years ago was The Fundamentals of the Course of Stars. It was called the Book of Nut because, you know, the first Europeans that started reading this text sort of saw that the figure of Nut, the night goddess, was very common here and sort of thought about that. So it is found in the Osirian and Abydos, you know, at this temple to Osiris, and also the tomb of Ramses IV, and some later papyri have some bits of it, and that's where a lot of our information comes from. And so it discusses various astronomical phenomena, including movements of the beacons being the stars that are defined, you know, whatever they're called in the diagonal star tables. And it seems likely that its progenitor text dates to the Middle Kingdom, so closer to like 2000 BC, in line with those diagonal star clocks or diagonal star tables, which would be interesting because then these two texts would probably be in conversation with each other. And it also has a really important religious text that links sunrise and rebirth, which is a real staple of, you know, ancient Egyptian religion throughout the millennia. But is not necessarily informative for us as astronomers, sort of trying to identify some of those stars with the actual stars we see in the night sky. So what does it look like? So the Book of Nut, so here it's from the cenotaph of Seti I, who was actually the father of Ramses II. If you know who that is, he was one of the bigger pharaohs, but nevertheless, I digress. So it's from his monument at Abydos, again, associated with the god Osiris. And so what we see here is the sky goddess Nut sort of stretching over the earth, which is very commonly how she was represented. She was representing as stretching over the earth. The earth was unusually in some ways represented as a man. It was the god of the earth, Geb, who was her husband, and the god of the air, Shu, was sort of separating them because that's what they saw around them, right? You had the earth, you had the air, and then you had the sky. And so the bits that are interesting to us sort of are on the edges here. They sort of describe what they saw as the topography of the sky, the daily course of the sun, the actions of the sun god, which is in some ways synonymous with the sun, the actions of other deities, but also the actions of beacons, which are these stars that are sort of listed in the diagonal star clocks. And in the middle here, we have what's called the dramatic text, which is an argument between the goddess of the sky and the god of the earth. And the argument was about the fact that she kept eating her children because that's how they perceived that the stars moved. The stars would move across her sky because she would sort of eat them in the evening and give birth to, or she would eat the sun god in the evening and give birth to him in the morning. This is how he was reborn every day. And for the stars, it was sort of opposite, right? Because they were visible during the nighttime. So that's more of an interesting religious detail that may be interesting for us, but nevertheless, it adds some character to it. And when I say that it describes the actions of these beacons that we are interested in, it gives a pretty precise cycle that they went through, but not described in words that we necessarily associate with actions that stars perform when we look up. So the beacons are first, whatever that means. They spend 90 days in the west. Okay, that seems kind of straightforward. They have spent 70 days enclosed by the Duat, which is the Egyptian underworld. They are born. They spend 80 days in the east, and then they spend 120 days working. So traditionally, how this was interpreted is that when they are in the Duat, in the underworld, they're under the earth. There are 70 days when, for example, Sirius is invisible, give or take, around the latitude of Luxor. And so what that meant is that was describing when the stars weren't visible at all in the night sky. But the 120 days that they spent working, because they were sort of the 12 hours of the night and the 12 rows in the diagonal star clocks, people interpreted that to mean that for 120 days, they mark the hours of the night. How they mark them? By transiting, maybe. These are some ideas that have been put forth. And it all kind of makes sense, but when you try to map it in, say, a planetarium software, it's never quite spot on. It never aligns as nicely as we want it. So there's certainly work to be done there, and there's a general model that exists, but it's something that that might benefit from being looked into a little bit more. And now, finally, we get to what I want to talk to you about today, which are the Ramesside Star Clocks. So remember that these are the latest, and they are found in the Valley of the Kings. So they are there are 4 versions of them, and only 4 that we know of. So there's one in the tomb of Ramses VII, the tomb of Ramses IX, and then there are 2 versions in the tomb that Ramses V and the 6 had to share for years. And so this gives you an idea of why they're called Ramesside star clocks. They're only found in the tombs of these pharaohs called Ramses that ruled sort of close by together, which would mean that for whatever reason, astronomical diagrams were all the rage. And these ones in particular that were never seen before and never seen again. So that's kind of interesting to start with. So there are 24 tables like the one depicted here that I'll explain to you in more detail in a bit, and each of them spans 15 days. So 24 tables times 15 days, that's again 360 days. So that describes a year minus the epigomenal days. So the days upon the year where you sort of get drunk and maybe don't mind the sky as much. But maybe they're sort of implicitly included in table 24. It's not really clear, but that's something to figure out. In the presence of this human figure, one of the things that sort of suggests to us that, oh, this was somehow observational. There was a human doing these observations. It's not just a description of gods and deities moving in the night sky. There is a human present. And so I think that this makes them a really great start to reconstructing the timekeeping model behind this data. And hopefully any insights that we get from this, we can then share to analyzing both the diagonal star clocks and the Book of Newt. So looking at them, this is a sketch of what they look like. So what we have here are the names of the different asterisms, so whether that's a singular star or a constellation or whatever they're naming. And also it tells us the day and the month. So it says something like on the first day of the month of Achet, which was one of the months the Egyptians had, or or something like that. On the left here, we again have hours now starting at 0 and culminating in 12. Any Python developer would be thrilled at this because we love to index things starting at 0. But this again describes sort of the beginnings and the ends of the 12 hours of the night. And on the top, we have these positions, and the positions are taken relative to the human body. So being an astrophysicist, I like to give them numbers. I didn't come up with this, but I like following this trend, which is that the central position is called 0, and then it goes to -3 on one side and -3 on the other side. And all the positions are given relative to this human body, which is another thing that makes us think that, oh, these were actual observations that, like some amateur astronomical society was doing in ancient Egypt around this time. And the positions are given here in Middle Egyptian, but fret not, you don't have to read the Middle Egyptian. What is basically key here is that the central position is above the heart. So the heart is the center of a human body. This heart is what they considered as the center of all knowledge and understanding. So above the heart. And then they could be above the right and left eye, above the right and left ear, and above the right and left shoulder. So that's what these positions here correspond to. And so this is what we sort of understand about them. Now we want to figure out exactly how these observations were done to produce these star charts. And for that, I want to use my good friend Python, the computer language, because I love studying things with Python. I think it's great. So again, our ultimate goal here is that if we can find the observational model that they use, like where were they looking, which stars were they choosing, things like that, to reconstruct these Ramesside star clocks, then we can ideally invert that model, right? And try to say, okay, the star that they call He Who Is in the Boat looks like it's, Vega or something. It's not Vega, but, let's pretend. And so we can reconstruct this relationship between individual stars and their Egyptian names and constellations and put a little bit more of sort of the Egyptian understanding of the night sky back into it, which I think would be cool. That being said, I am always led by this quote by George Fox, another fellow Brit and statistician, that said, all models are wrong, but some models are useful. So whether it is the observational model that I'm creating with Python or the one that they are using, I have to be careful that I can never 100% know what star they are referring to. I can say it's likely they're referring to a certain star, but unless there is, you know, some text somewhere that we unearth that sort of like draws a parallel between Egyptian stars and their, you know, Greco-Roman counterparts or something like that, we'll never know for sure. So that's just something to keep in mind. Okay, so we're all here to talk about stars. So how do we do that? How do we study the Egyptian sky and the Ramesside Star Clocks with decanOpy? So decanOpy is a Python module that I wrote for, you know, archaeoastronomers. So, and it's used to find positions of stars above Luxor about 3,000 years ago. And to do that, we need to specify what's called a precession algorithm. So you folks might all be familiar with this. Some of you might not be familiar with this, but just in case, I will go through it. So precession refers to the effect that the tilt of our Earth is sort of wobbling in space. And this comes from all of these sort of what's called tides by, you know, the sun and the galaxy and stuff like that. You know, there's a lot of gravity out there and sort of causing us to wobble. So right now we live in a great time because our northern pole points towards Polaris. And that's incredibly useful. It's incredibly useful to have something like the North Star and to point at it and to go towards the North Star if you're trying to find your way somewhere. 4,000 years ago, that wasn't true. The North Pole wasn't pointing towards Polaris, and it wasn't pointing towards Vega or Alpha Draconis or Deneb either. It was just pointing at an area of sky that was kind of sparse. So that means that the sky was a little bit shifted from what we see. There are a few ways to calculate this, and astronomer called Von Drack put forth an algorithm that's pretty precise for something like 30,000 years or 10,000, a length of time that is way longer than what I'm interested in. So that is what we use to sort of shift the current understanding of where stars are to where they would have been about 3,000 years ago. We also calibrate to Stellarium, which is a wonderful planetarium software, so that we can also do quote unquote reasonableness checks. That is to say that whatever my Python code is spitting out at me, I can compare that with Stellarium to make sure that we're getting, you know, similar answers and that the sky looks reasonable to me. And what my code really gives is local observer coordinates. So it gives me an altitude and azimuth, given the understanding that I'm observing from Luxor. This can be changed, but right now we're only considering them doing the observations from Luxor because that's where the Valley of the Kings is, and you know that's where these texts first appear. Of course, there's nothing to say that they couldn't have done the observations at a different time or somewhere else and just had a bunch of charts, you know, drawn up somewhere that collected dust for 1,000 years, and then one day a pharaoh saw it and went, "That's cool, slap it on my tomb." That's possible, but right now we're only considering that they were created around that time and that they were doing observing from Luxor. Right, so we want observer-centric coordinates, and we have an ability, which I think is really exciting, to create synthetic Ramesside Star Clocks. That is to say, if I give my code some assumptions, like assume they're observing at Luxor, assume it's 1300 BC, assume they're looking due south, and they're looking at the transit of the brightest star that is available in like a 10-degree window. What kind of Ramesside Star Clocks would that provide? And then we can compare those to the real thing to try to get some answers. So here's some assumptions that we're testing. So how wide is the horizon, right? The stars can be, you know, above all of these body parts from the left shoulder to the right shoulder, but how far away is that? Right, which equivalently, where is this human figure located? Is this a friend that I had sit down at a, you know, designated spot that I marked by chalk and I'm standing 10 feet away from him and looking at him and looking at, you know, how far the sky is subtended by his shoulders? Am I standing 20 feet away? Does it matter how wide my friend's shoulders are? Is it a statue that always stood in the same place? It's not clear. So what we want to do is sort of play around with how wide that horizon may be. Maybe it's 5 degrees, maybe it's 10 degrees, maybe it's 15 degrees, and see how that affects the kinds of observations we would make. Where is the central position? So are we looking due south and looking at stars transiting? Are we looking due east and looking at them rising? Are we looking due west and looking at them setting? Are we looking somewhere in between? All of these are options. It's not described in the text. Also, are there gaps between these bins, right? So these stars are telling me where whatever star is named here is in the 0 through 12th hour of the night, but is there a hole in between? Does it have to be directly above my eye or directly above my ear? What if it falls in between? Do I count that or do I not count that? And also, how high can the star be and still be useful? Like, what is my altitude window that I'm considering? If I'm looking at transits, you know, I'm just looking at them going over, and so that will directly be related to their decanOpy measurements. But if I'm looking, say, east and looking at stars rising, I probably don't want to look much farther than 10 degrees, 20. At what point are they too high up to actually mark the hour and to know, oh, that is the star that like reached that point right now? And also there's just a ton of human choice. If more than one star is in a position that I could feasibly choose, do I choose the brightest star? Do I choose the star that has the biggest religious significance to me? Do I choose the central star? Because there's a lot of central stars. We see that they liked that, and I just like them to be above the heart. Do I have other choices that I'm implementing that I haven't even thought about? There's the statistics of our night sky here, but there's also the statistics of human choice, which is sort of hard to get at. And so we're trying to think of clever ways to do that. So just to summarize, so our observational model is what we're testing. We're looking at things like horizon size, the observing direction, the altitude window, the bin and gap size, but we're also looking for human choice, like brightness of stars, significance of stars, preserved position in the table, etc. Now, thankfully, because there's 24 of these tables for a year, and then times 4 because they appear 4 times in 3 different tombs, we can kind of do statistics about this. So we can look at all of those, the real data that exists out there, and say, okay, what is the preferred position in the bin, right? What are the preferred positions in the real data? And so this is just counting up how many stars appear in the central, you know, above the heart, above the eyes, etc. And we see that they really liked it to be above the heart. Is this because of the direction they were observing, or is this because they chose to make it this way? That's something that we can try to test. They sort of liked the eyes a little bit less, but pretty equivalently between the left and right eye. But then we see that they liked the right side a little bit more than the left side. And also we see that they liked the left shoulder more than the left ear. So there's a bit of a skewness to this data, right? And so what we ideally want to do is try to reproduce some of the statistics of the real data with our fake data, and then say, okay, it looks like this observational model is a little bit more correct than the other one. Yeah. And so we set up 3 types of simulations. First, we simulated the real sky, right? Because that's the sky that we'd be looking with. We have real and bright stars. We choose stars from the Hipparcos catalog, and we choose stars that have a magnitude that is larger than 4. Now, of course, humans, you know, in very dark conditions, as they surely would have been in ancient Egypt at this time, they can see a fair bit less bright than a magnitude of 4. However, our assumption is that if I'm building, you know, a star clock out of these stars, I want them to be really, really obvious. And so I don't want them, you know, I don't want to have to like squint to see them. We also created a band of Sirius-like stars. So Sirius is one of the stars that appears in those names that we can actually identify. So clearly they like Sirius, and plenty of reasons to like Sirius. It's religiously significant to them. It's associated with one of their deities, but also it's a very bright star. Why wouldn't you use Sirius? And so we say, okay, what if the sky was just a bunch of Siriuses, you know, with different RAs and a cycle around here? Now, this is a weird case, but it's almost a human choice only case. It's like, okay, what if this is the perfect star? Would they be happy if we had a sky just full of Sirius? Would that have been helpful to their observational model, or does that tell us something? And then finally, we simulate a totally random star field. So it's a sky that we could have had if our universe was just a slightly bit different, right? If there was a different statistical realization of our universe, but it's not the sky. And so this ideally contains the same statistics of the night sky like the one that we look at, but not necessarily of the human choice. We don't have biases towards these stars because we've never seen them before. It's not the sky that we look at. And so just as an example, I will give you the two versions of Ramesside Star Clocks, synthetic Ramesside Star Clocks that we faked to compare with the real thing. And this is for the Sirius-like data. So this is what if the sky was just Sirius 24 times around in a big belt. And what I'm showing on the left here, so this is a table for January 1st through 15th. And here is July 1st through 15th. So like deep winter, deep summer, 1300 BC, just as an example of a year. And we're looking due south. So we're looking at the transits of Sirius and Sirius-like, if you like. And so S00 here is the real Sirius that appears. and doesn't appear in the summer because it is under the earth, it's not visible. But just at a glance, if you look at where the stars are possibly located in these tables, you can see they're in all of these sort of vertical lines. That doesn't, and none of them are in the center. Well, very few of them are in the center. That doesn't look like the data I just showed you, the real data, right? And on the right here, it looks like a right mess. And again, there's not that many of them in the center, which we really see that they really like the center. And just to convince you, I've done statistics on the 24, fake star clocks that we produce, and their statistics look like this, which is not at all like that central peak we were seeing before. So this is just one of the examples of the runs that we've done. The real sky and fake sky runs are a little bit more interesting, and we hope to be able to finish analyzing that data and writing our publication sort of by the end of the summer and in the early fall describing this. So with that, I hope that taste of what we are doing, creating sort of these like these synthetic versions of really ancient data was interesting to you. But just to wrap up, so we don't know the exact observational model that the Egyptians used to generate these Ramesside star clocks, or indeed any of their star data. But open source digital tools like decanOpy, especially based on sort of modern astronomical software, can really help us begin to elucidate the possibilities. So making these fake or synthetic Ramesside star clocks is a promising direction. And the ultimate goal is to map the Egyptian names of stars and asterisms onto our night sky with some probability, not completely deterministically, and be able to see the night sky as the ancient Egyptians saw it. So the last time I gave this talk, I gave it to a bunch of people interested in archaeology and Egyptian heritage. And so I just wanted to highlight that if the sky is heritage, it is also heritage and danger from light pollution and stuff like that. And so I advocated for people to get involved with light pollution or dark sky conservation. I don't think I have to tell that to this group, but I left the slide in just because it's a cause near and dear to my heart. And I wanted to say, if you just can't get enough Egyptian astronomy, Sarah has this wonderful video on YouTube. I encourage you to check it out. She's really amazing at talking about this stuff. And then finally, just an extra thank you to the ASC for having me today. Unfortunately, you kind of just missed me. I was just in Edinburgh about a month and a half ago. So, hello from the castle, hello from the Johnny Walker Whiskey Tasting Tour, because I'm a tourist. And also remember that the National Museum of Scotland has some really, really wonderful Egyptian artifacts. And I wanted you to say hello to this hedgehog because he's very cute. And unfortunately, I took no photos of any of the astronomical data. So thank you so much. I hope you enjoyed that, and I'll take any questions.
Thank you very much, Gary. Thank Luna for a talk, first of all. Thank you. Really fascinating stuff, Luna. Thank you. If you want to put your name in the chat, if you've got a question, or you can just speak up if you've got questions for Luna. And if you're on YouTube, put your questions in the chat there, and someone will pick them up as well. Yeah. You got any questions?
Well, I can fire off a question, Mark, if that's okay.
That's fine. Carry on, Mike.
Hey, Luna. I enjoyed the talk. I was particularly fascinated by what you said at the end, where you were talking about coming up with probabilities for the different models. And a critical part of that is how you quantify the difference between the maps that you created, which are peaked around 0, and whatever you get. So my question was going to be, how are you planning to quantify that difference to convert it to a probability?
Right. So I think I should apologize here for being a little bit fast and loose with the term probability, because of course this is a gang that would be have an understanding of statistics and sort of what it means. So I don't foresee doing any sort of like best chi-fit, sort of like within 3 sigma sort of real probability. I guess all I meant to say is remind everybody that no matter how much I can recreate these numbers using, some guesses of an observational model, even if my observational model is bang on, there will always be that element of human choice of sort of like, which star do I choose? And so I can say, well, we can recreate all of this data if we assume that they're looking, I don't know, 20 degrees west of south, and watching stars, like transiting, up to 15 degrees high in the sky, and they're choosing, in that case, like for each of these hours, here's a snapshot of the sky they would be looking at. They probably chose one of these stars. And, if it were my guess, I would take the brightest star out of there, or I would take one of these two stars, but there's nothing to say that they would have made those choices. So I just meant to say, like, again, as George Bach said, all models are wrong, some models are useful. I hope it'll be a useful model to think about it, but I can never 100% say, aha, this is the star that we're looking at. So when I say some probability, I mean that in a qualitative social sciencey way, rather than like a quantitative astronomical, like fits to CMB data sort of way.
Sure.
Does that answer your question?
Yeah, it's fine. I mean, I realized you were talking to a blank box because I didn't start the video. But, thanks for the answer. I mean, yeah, the whole thing is interesting how you do it and whether you might be able to get something out of it with comparing distributions. Don't know. But obviously, you can tell from my question, I've done some stuff on inverse problems before. So that's where I'm coming from.
Yeah, I'm definitely trying to bring my sort of like hard science astrophysicist, let's do math bend into it. As you can see, that's where the whole let's use Python things comes from, right?
Yeah.
But I'm also trying to reel myself back and be aware of at one point I'm just overextending the applicability of the model or the tools that I'm using.
Sure.
So it would definitely be awesome if I could think of some way to sort of like very sort of like formally statistically compare, like, say, the different types of models that give me approximately the correct heuristic. In this case, I'm just showing you a binning, right? Like I'm just showing you a count per bin. But we're also trying to come up with, sort of different heuristics, like how many individual stars are used across all of them, because the stars repeat, right? And so I believe in the original data, they use something like 47 individual stars, which seems about right. That's, basically 24 times 2. So that seems like a good cohort of stars. And so when we're applying some of the human choices, we say, okay, if I only choose the brightest star looking in this direction, how many unique stars do I choose and stuff like that? So it's definitely statistics inspired, but sort of like pumping a bit of the brakes before making claims that I can't hope to back up.
A great master's project if you get a good student that you can just send off and explore these different choices.
Oh man, I wish, but first they have to get a faculty position. So spread the word.
Okay.
Spread the word. I'll move to the UK, have someone hire me. I will absolutely do a master's student project on this.
Cool. Thanks.
Absolutely. Thanks so much.
Ian, you have a question? You want to ask it?
Yeah, I'm just wondering if you can go in a sort of reverse direction, looking for known events like supernovae and trying to pinpoint them in those records, which might actually help to decode those records.
Yeah, so definitely one useful thing would be something like supernovae or even eclipses. But to my knowledge, and I may very well be wrong here, but it wasn't obvious to me that there were very clear records of that. There was some work done recently that sort of looked at stories from the Bible, from the Old Testament, and sort of identified one of the events being described in rather like flowery poetic language with a eclipse, which would have happened around that time, and therefore used that to sort of say when the rule of Ramses II was, assuming that he was the pharaoh in the Bible, or it was something along those lines. Let me not misrepresent this research. That would certainly be a great way to go, but I don't know of a wealth of primary data that exists recording things like that. But, every so often they look at like some monastery in Cyprus and find a null papyrus and find an end to a story that we've been looking to add for 50 years. So there's always the possibility that that type of data from Egypt is unearthed. And I think that would be really exciting because that gives us, a very absolute timekeeping that we can then compare all of the relative timekeeping sources to. Because, when your timekeeping is sort of like in the, 23rd year of the reign of, like whatever, Senwosret III or something like that, that's really good relative to other events, but sometimes it's hard to pinpoint to sort of like an absolute Gregorian style calendar. So there's definitely people that are thinking about that, but I believe there's been more work done with ancient Chinese astronomy on that because they believe they had better records.
So these tables,
but that's a great question.
So these tables that you're studying, they only record the position of stars.
Right. So that, they look exactly as what I've shown you, which is not to say that this is all the astronomical data from ancient Egypt. This is just the one that I sort of chose to focus on. But so these are sort of widely interpreted as I described them, which is to say, position an hour. In this case, the position is relative to a human body. But if you're looking at something like these, the position is less obvious because it tells you an hour versus a week, rather than having, one of these with like a direction for, every week, rather than having 36 of these then like per position. So it's almost like a matrix problem, right? You're looking at these sort of like yield spreadsheets and trying to figure out exactly how they were put together and what the idea behind them was, which is the bit that I find really exciting.
Okay, thanks.
Thank you.
Other questions on Zoom?
Could I just ask whether or not there's anything in print that we could actually get our hands on to read about this material?
So yeah, so actually I was just talking to Sarah Simmons, my collaborator, about this. A lot of stuff is unfortunately paywalled. So the sort of the text that everybody falls back on, there are 3 volumes of Egyptian astronomical texts by Neugebauer and Parker from, I believe, 1960. These books are extremely rare, so have a look around your local libraries. But if you can't find them, there may or may not be PDFs around the internet that you could download, that I'm not telling you to download, but they exist. Recent scholarship, a lot of it is in German. So there are several German scholars working on this that do really good work, including Alexandra von Leuven, who was the first to to figure out that the Book of Newt was actually called The Fundamentals of the Course of Stars, from translating a new bit of text that hadn't been translated before. So that was really excellent. So if you read German, looking at some of those might be useful. But otherwise, I will really point you to a lot of Sarah Simmons's work. A lot of it is available online, and she does really, really fantastic stuff in a lot of overviews of other Egyptian star data. Belmonte and Lull is also, there's a book on ancient Egyptian stars that they wrote, I think recently. It was 2021, 2022, I think. So that is another thing to look up. I hope those were some helpful bits of, some helpful breadcrumbs that I've sent you in search of.
Okay, thank you. Anyone else on Zoom? Will, is there anything on YouTube?
No, there's nothing on YouTube, but excellent talk. Thank you.
Thank you.
Well, if there's nothing else, then can we thank Luna again for that excellent talk? Thank you, Luna.
Thank you all. I enjoyed talking to you today.
Thank you. And apparently Canada is having a heat wave at the moment, like us here, but that's coming next week for us, isn't it? Next week. Really good, thank you. Okay, that's it for this evening. We'll be back again at the start of July with our next talk, and hope to see you all in person then in Edinburgh and online if you can't make it. So thank you again, Luna, and good night, everyone.